Good afternoon. I make this presentation on behalf of my colleagues in HP Labs and HP Storage. My name is Ajay. I'm from India. And the solution that we describe today is implemented on the HP Advanced File System, which will be out in a product the next couple of months. So where I come from, we have a saying that goes, would you cross a stream in a ship? I would rephrase that as the rhetorical question, would you use the Titanic to cross a river? The answer to this question will emerge in the next 20 minutes, so hang on. So what do we mean by FailureAtomic Updates? Through FailureAtomic Updates, we would want applications to make their data structures persistent and consistent. A typical application opens a file, modifies its contents, and when the contents are in some consistent state, would want to atomically flush the contents to stable storage. In this example here, we have the big boxes, which are called atomic sync points, and these are the points where the data structure is in some consistent state. In the example, I have a linked list, but it could be your favorite data structure there. IOs need not be stopped between any two sync points. All that we require is a mechanism in the eventuality of a failure to revert to the previous successful sync point. So in order to achieve this, what interface would application developers want? Naturally, they would want one that deviates the minimum from what is used today. So this defines our usage model, and we'll come back to the usage model in a couple of slides. So when we talk about failure atomicity, the first thing that pops up is relational databases. They are rich, feature-rich, and they are powerful. But if all you want is atomicity, are they the right choice? Take, for example, an in-memory data structure, like a linked list or a tree. There exists an impedance mismatch between updating these in-memory objects and the relational model that results in back and forth translations among the two models. And finally, recent work has shown that many databases are inconsistent after power cycle tests. This is rather surprising. I urge you to read the OSDI 14 paper by Zheng and colleagues to understand more about this. That's my favorite quote. Not everything that is big and complex is necessarily safe. Another mechanism to failure atomically make changes is to use key value stores. The problem is that you application developers have to shoehorn read-write accesses into get-put interfaces. And key value stores also lack the declarative expressiveness of SQL. The typical method used by application developers to get atomicity is to use the rename system call, because unfortunately POSIX does not give an atomic write interface. This involves making a copy of the file, modifying the working copy, and once the working copy is in a consistent state, rename the working copy back to the original. These steps are punctuated by well-placed fsyncs, and if these fsyncs are not placed at the right places, bugs can creep in. And naive copying files, especially when the files are large, can be slow. There's a lot of research in the recent past on failure atomic updates. Fusion IO provides a write-v call that is pretty neat, but the problem is that you require Fusion IO. You require the hardware for it to work. Valor provides transactional interfaces in the file system, but the log append needs to be called before you make any modifications, and that is not very intuitive. Microsoft's TXF provides extensive transactional interface in the file system, in the NTFS file system, but the complexity of the interface has resulted in lukewarm response from developers. FailureAtomic msync is work done by my colleagues previously. The problem is that updates are limited to the size of the file system journal, and it allows only mmap and msync. So the work that we present today is inspired by FailureAtomic msync, and what we present today is a better and a more generalized solution. So now we come to our solution. It's called OAtomic. All you have to do is pass an OAtomic flag while a file is opened. And lo and behold, every subsequent sync system call becomes atomic. This is implemented in HP's advanced file system, as I mentioned before. We have also implemented a syncv system call by which multiple files can be made atomic. So here the white and green circles are the atomic sync points, and we achieve this using existing system calls, msync, fsync, and fdatasync. In the event of a failure between any two sync points, the file is rolled back to a previous sync point. So coming to how we implemented this in the file system, we use clones, which are writable snapshots. So when we open a file with OAtomic, a clone of that file is made under the hood. When a modification occurs to a file, we use a copy on write mechanism, and the original file gets a copy of the block, whereas the clone points to the original block. And when the user calls a sync, we delete an old clone and a new clone is created. So we see that a clone at any point, if it exists for the file, is the atomic version of the file. Recovery happens lazily on lookup. If a clone exists for the file, then we delete the file and rename the clone to the file. This can be easily implemented in any file system that supports writable snapshots. We tested correctness using crash point tests and power cycle tests. Crash points are specific macros placed in the code that causes the file system to panic at that point. For power cycle tests, we use an external scriptable device which randomly cuts power to the machine. Our tests show that there was no corruption when we use OAtomic. So we tested the performance of our implementation against existing key value stores, and I need to mention that we just slid OAtomic under a standard C++ STL map interface and made in-memory modifications and called msync. Our performance is comparable to existing key value stores. These are the caveats of our implementation because we use clones, which is a version of snapshotting. We induce fragmentation in the file system. Online defragmentation helps, and we do have that in the HP advanced file system. Multi-process updates needs to be carefully coordinated by the application. In conclusion, we provide a very simple interface. It is simple to use for application developers. It is simple to understand and implement for file system developers. So I'd like to conclude by asking the question, would you use the Titanic to cross a river? Well, if Kate Winslet is on it, maybe I would. Otherwise, maybe not. May not be worth it. So that concludes my talk, and take questions now.
I'll start with a question. Have you evaluated so you mentioned it will fragment the files, but have you have any idea of or evaluated when you're going to deploy this, how much fragmentation will there be, and how much background fragmentation will maybe kill the foreground IOs and so on?
Well, not really. We've not done an evaluation on the fragmentation. I guess it would matter when the free space in the file system becomes less, right? We have not yet done an evaluation on that.
Justin Mazzola, Pluska, editor. So you said that multi-process coordination is complicated. Why is that?
The reason is that just as multiple processes would access a file, right? You need to, first of all, take care of the concurrent accesses to the file. The other problem is that within the Linux kernel, we have the file open through multiple processes. And if one of the processes crash, we still have the file open, the handle open through the other process, right? So there's no easy way to detect that one process crashed. On the other hand, if it is a single process that has opened the file and that process crashed, we would lose access to that file descriptor, and the next time we would open the file, we would recover it.
So what I'm trying to understand is, do you make it worse than the existing status quo? Or, because that's where I know multi-process coordination can be difficult. I just don't understand where the difficulty comes in with this work. I mean, I can understand not being able to know when a process dies, though that's difficult. You could do it some other way, but I'm trying to figure out what makes this especially hard with your technique. Are there new things that I have to worry about now that I didn't have to worry about before?
Right. There is some extra things that you need to worry about when you use this, apart from coordination. Yes.
John Osterhout from Stanford University. I'm just curious about the performance implications of this. If I have a large file and I make a small set of changes, is the overhead for the cloning inexpensive? And then conversely, if I have a large file and make a lot of changes, is the sync operation extremely expensive?
Well, for small files, the overhead is not much because we use a copy on write mechanism for the clone. So only the block that is modified gets cloned. For large files, if you're doing the sync after modifying the file immediately, then there is an additional overhead.
Is the overhead related to the size of the file or to the amount of data I've changed between syncs?
It's related to the amount of data that you've changed, not to the file itself.
Thanks.
All right, I guess let's sing the speaker one more time.